Okay, so either today is Amelia Holcomb. Amelia is a PhD student in computer science and plant sciences, and she's been working for the last couple of years on using GEDI for measuring all sorts of things. And today she's going to talk about small scale crop disturbance. And this is a presentation she actually also did at Simulator.
I did that one in 12 minutes, so you guys are in for a treat.
Yeah.
Just gonna do my slow southern drawl and for the whole thing, and we'll spread it out to 40. Okay. Great. So thank you, Kesha. As Kesha said, so my name is Amelia, and I'm going to be talking about my work on measuring small-scale tropical forest disturbance with spaceborne LiDAR. Okay, so there's a lot of things to unpack about that title, but let's start by talking about what is forest disturbance. So we can think about deforestation, which is maybe something that you're more familiar with. So deforestation is defined by kind of complete biomass loss or almost complete biomass loss and a transition to a different type of land. Whereas disturbance is defined by a partial biomass loss, but the area remains considered forested land. And so, for example, some significant causes of disturbance in the tropical areas that we're working are selective logging, so where you're just cutting down some of the trees in an area, but not clear cutting. Fires, which often won't reach all the way to the upper canopies, and we'll talk a lot more about that. Storms and drought. And many of these are of particular interest to us because they're becoming a lot more important and a lot more common every year. So we know, for example, that the area of disturbed forest is expanding every year. We know that in the Amazon basin, the area of disturbed forest and degraded forest has already surpassed the area of deforested regions. And we know that some of this increase is because of global warming. But also some of it is because as countries are making pledges to shift away from deforestation, it's increasing pressures towards degradation like selective logging. And to be clear, like that is a better alternative often to clear cutting. But it does mean that it's something we need to start understanding much better than we have historically as a result. So disturbance is difficult to detect from satellite imagery, but there have been really big advances in this space in the last 5 years or so. And we're now getting pretty good at detecting disturbances from satellite images. But one big research gap that remains is that it's still very difficult to estimate the carbon emissions that are associated with disturbance. So global estimates for disturbance carbon emissions in the tropics range from 40% on the one side to 212% on the other side of the emissions due to deforestation. And that's kind of like some of our best estimates right now, right? And disturbance is also complex because unlike deforestation, where you sort of understand what happened, there was forest and now there's really not a forest. Disturbance leaves a forest there, right? And it's complex because it can affect that remaining forest structure in very different ways. And thus it's affecting the habitat and the ecosystem that remains. And this, as you can imagine, is even harder to measure using existing satellites. So we're going to get into that structural question in a moment, but first I want to introduce these two state-of-the-art products that can detect disturbances across the tropics. So the first is called RAD. It's based on Sentinel-1 radar, and the second is called AFC, or I'll sometimes call it the Van Clitsum maps. These are based on Landsat optical data. And for those of you who aren't familiar, I want to talk briefly about Landsat. So Landsat is a long-running satellite sensor. It's got data from about the 1990s, so it's been getting better and better in quality over time. And it's also what we call a wall-to-wall sensor. So what that means, and Sentinel-1 actually is also a wall-to-wall sensor. So what that means is it covers the whole surface of the Earth without gaps, really. And so by kind of stitching together what it's seen across the whole surface of the Earth, we can get this continuous image with like square pixel resolution, like a giant picture, right? So those are some strengths of Landsat, but its main limitation is the technology, which is called the passive optical sensor. You can kind of think of this as just like, it's like a really good camera that you can use to take pictures of the Earth. But what that means is that it's looking down from the top, right? And when we think about the Amazon rainforest, the rainforest has an incredibly complex and layered structure, right? It's got an upper canopy, but then below that, it's got distinct middle canopies, and it's got an understory that actually has got a lot of vegetation in it. And like I mentioned, right, disturbances can have really different effects on those different layers of the canopy. And so just looking at Landsat, you're going to have a hard time understanding what's going on below the canopy and the ways that those different layers are being affected. So this is where GEDI comes in. GEDI is a spaceborne LiDAR system that's mounted on the International Space Station. It's brand new. It only just started collecting data in 2019. It has 8 laser beams that are pointed at the Earth's surface, which take samples across the Earth's surface every 60 meters along these 8 lines following the orbit of the International Space Station. And when GEDI takes a forest sample, it sort of washes this small area with a laser pulse, and it receives back the shape of that return pulse as it bounces off of whatever structure is there. So some of this pulse is going to bounce off the top of the canopy, some of it's going to penetrate through, and it's going to bounce off of the mid-story and understory vegetation, and then some of it's going to get all the way to the bottom, to the ground. Even in these dense tropical forests, it's going to bounce off the ground and return. And so by analyzing that return waveform, we, or I guess more properly NASA, can measure the height, the density, and the structure of whatever the laser pulse sample. So specifically, we can use GEDI to measure canopy height. We can use it to measure biomass, and this kind of translates directly to carbon. So this is how we're getting a sense of carbon emissions, is by measuring biomass. And we can also measure the vertical structure. One of these key metrics is called plant area index, which we're going to be coming back to at the end of the talk, but it's sort of a sense of kind of the vegetation density in an area. And one thing that's really important to this study is that GEDI is a sampling mission. So it doesn't obtain wall-to-wall data for its coverage region, like Landsat or Sentinel-1, but rather it's collecting information about these 25-meter diameter footprints, which are also called shots. And as I'm showing in this clip on the right here, it also doesn't regularly re-measure the same locations with any fixed or frequent repeat cycle. So it would be very difficult to use GEDI to detect disturbances or to measure changes that are associated with any given individual disturbance. But here's our proposal, that we could combine these disturbance detection maps with the incredible quantity of data that GEDI has collected. So even though the GEDI mission doesn't have a guaranteed repeat cycle, it did sometimes happen to measure nearby locations twice. And sometimes a disturbance event happened to occur in between those 2 measurements. And that disturbance event was detected by the RAD or the AFC maps. And if we could identify those events, we could create a large-scale opportunistic sample of before and after measurements of forest disturbance. And this is going to be a sort of needle in the haystack search. So to recap, what we're looking for, bear with my fun cartoons here, what we're looking for is we have one GEDI shot, and it's measuring the pre-disturbance state of the forest. Then a disturbance event takes place, and that is detected by the RAD or the AFC products. Then a second GEDI shot, which we're going to allow to be up to 40 meters away from the first, falls essentially right on top of the disturbance, and it measures that disturbed forest. And we decided to start by looking at the Amazon biome from 2019 to 2022. So there are several questions that have come from previous work around measuring forest change with GEDI. And the first question that, frankly, I think should be on everyone's minds at this point is this analysis going to be possible at all? We are talking about measuring pretty small things using a giant laser from outer space. So, and in fact, in the original paper on GEDI, proposing GEDI, the NASA team stated very clearly, we are not sure that GEDI can be used for this. And then even more recently, some recent concerns were raised in this 2021 paper by Roy et al., which we're going to keep coming back to. And this paper found that in disturbed forests specifically, which have these very heterogeneous canopies, right? Like something was cut down over here, and then over here it wasn't cut down, right? So there's just huge changes in a very close vicinity. Just the imprecision that's inherent in the GEDI sensor about where exactly that footprint landed on the surface of the Earth could cause variation in the canopy height measurements that you make that could be as large as the changes that you were hoping to measure. So I guess they didn't say it's impossible, but they said, you know, we tried one natural way of approaching this and it didn't really work, so be cautious about this type of analysis. So an encouraging way to start. But let's say if this works at all, I think our second question is whether GEDI could do what it promises. So not just tell us about canopy height losses, but actually look under the surface, under the canopy, and reflect some of these more complicated structural changes that are taking place. And I think there was one very interesting study that just used simulated GEDI data. So they didn't like kind of try this with the real data set, but they simulated what they thought would happen. And they said that they thought that GEDI might be able to measure, for example, sub-canopy fire, where primarily the understory is lost. So I'm going to say that's a maybe yes. And then the third question, I think, speaks to the broader goal of this study. So we know that we can't use GEDI to measure every single disturbance. But instead, what we want to do is build a data set of GEDI measured disturbances that were also observed by another wall-to-wall satellite, and then see if we could use that to extrapolate, right? So we're hoping that there might be some relationship between what, say, Landsat sees and what GEDI, like the percent biomass loss that GEDI measures. And the study of that question has been very, very limited, mostly because there's almost no data to look at it. There was one very nice but small field study called the Phodex project, where they actually went out and just cut down the trees themselves, and then looked at what they saw in the satellite, and they were like, well, was there any relationship between how much we cut down and like what the biomass loss was and what we saw? And they suggested that there might be a relationship, but that was based on 8 1-hectare plots across the whole world, actually just 2 locations in the whole world. So very small. Mostly, we just think that adding more data could go a very long way towards starting to even like think about answering this question. Okay, so focusing particularly on that first question, is it possible, which is going to be where I spend most of this presentation. Let's take a look at the methods. So we need to design our methods to evaluate, right, whether that's true. And we want to demonstrate, hopefully, either a definitive yes, GEDI can measure these disturbances, or it would also be helpful to get a definitive no, GEDI cannot measure them. And so we have what I'm calling the treatment group of coincident shock pairs with intervening disturbances. And we need to evaluate any effects that we see in that treatment group against some kind of control. So a simple control is just a pair of coincident shots without a disturbance. And what we're hoping, right, is we should find that in that case, the GEDI shots did not measure any forest loss. So in other words, we're hoping that we're going to see an unbiased one-to-one relationship between these 2 GEDI shot measurements that occurred about 40 meters apart in that case. And then we could say that GEDI seems to be measuring disturbances if in the treatment group where GEDI should have measured a disturbance, we're seeing a loss that's statistically significant relative to the changes that we saw in the control group. So this is our first control group. It's pretty simple to construct, and it's actually most of our coincident shock data, but in many ways it is not an ideal control group. Because most of those shot pairs, by chance, are going to fall in the relatively intact and homogeneous forests that cover most of the Amazon biome. Whereas the treatment group, by design, lies entirely in disturbed forests, which, whether or not a disturbance just happened, we expect that those forests are going to look different. And in particular, they're probably going to have a much more heterogeneous canopy, which is exactly what Roy et al. Kind of highlighted as a problem, right? This might cause coincident shots to look different. And so this control and the treatment group aren't exactly comparable. So to deal with this, we created a disturbed control group. So these are shock pairs in a place that it does experience disturbance, just like the treatment group. But the only difference is that GEDI didn't happen to measure that change. So either the 2 shots fell before the disturbance or the 2 shots fell after the disturbance. Okay, so far so good. Let's go find this coincident shock pairs. So here's where we hit a whole other and much more mundane side of the is it possible question, which is actually performing the computation. So I I would actually venture that one of the main reasons that the study of coincident GEDI shots has really not been done very much before, even though it's been suggested a lot, is because of the computational complexity that's involved in even approaching it. And that Roy et al. Paper only looked at a very small area in the Congo. And then because of that, that kind of limited the methods that they could use because they had such a small data set to work with. So to give you a sense of the scale of this problem, the raw GEDI files for the Amazon region during the time period we're studying, 2019 to 2022, is about 12 terabytes of data. Those raw files are organized in a way that I affectionately call anti-spatial. So every raw file corresponds to one orbit of the International Space Station, which means it's basically a line of data points. So if I want to find all the shots that are within 40 meters of some location, I have to look for them in tons of different files. And finally, even once we've done that, we still need to match the shot data with 4 years of 10 to 30 meter resolution raster data. So this is a huge computational problem. So I'm just going to do a little bit of unsponsored, sponsored content, which is to encourage anyone who's working with large-scale spatial data sets to take a look at Apache Sedona, formerly known as GeoSpark. If you've ever worked with Google Earth Engine or MapReduce, or Databricks, or if you happen to have worked at Google with Dremel or Flume, the programming paradigm will feel very similar to you. And if you've been trying to distribute or parallelize your data processing using Slurm or parallel, Python threads or R parallel, I think Sedona will feel much, much better. So essentially, briefly, Sedona allows you to write transformations, computations, and SQL queries over very large distributed data sets, potentially covering thousands of different files. And it's going to split up those queries and computations into natural pieces across lots of different worker jobs automatically that are controlled by a leader node. And you can very flexibly kind of distribute and rejoin the computation and distribute and rejoin and distribute and rejoin and kind of repartition as you need in a very flexible way. And unlike other frameworks, it understands geospatial data. So the queries that you write can be things like, find me all the points in this polygon, which isn't something that most frameworks that do this kind of distributed processing can really handle. And it can build spatial indices on the fly, which can really help speed up your computations. So with Sedona plus the other tool I use, which is PostGIS spatial indexing, we were able to find, okay, this is not a proper benchmark, this is just what we got on our hardware, but we found about 4 million coincident shot pairs with like 56 jobs. It took about 13 hours. And then matching this with raster data to find coincident shot pairs that overlap disturbance with 15 workers takes only about 2 to 6 minutes. So all of a sudden, this is actually manageable. You can find those coincident shots once, and then you can really do development very quickly.
Should we ask questions now? Or
You can, yeah, go ahead.
if 10 shots fell in the kind of the same region,
Yeah.
how do you, is that 10 pairs or actually,
Yeah.
or is it 10 times 9? Yeah.
So, okay, so the other thing that I didn't talk about is there are actually very clear spatial patterns in how the GEDI shots are distributed. So in the mid-range latitudes, that is extraordinarily unusual. So as you get further and further north or further and further south, you get like many, many more GEDI shots because that's where the space station turns around. And so you will get like, basically it looks like a time series. In the tropics, it is extremely rare to get any more than 3 shots that are together. And usually it will be like 2 shots in one orbit and 1 shot in another orbit and that's it. So it's actually, that's pretty unusual. We didn't really, yeah.
So are the errors increasing as you get towards the northern and southern latitudes because it's turning in all kinds of other factors in between?
Not that I know of.
Okay.
Not that I'm aware of.
It's not fact practice,
It's like
yeah.
arcing.
Okay, but the curvature of the earth is different, right, as it gets further up, so it's calibration must be falling off as well.
I don't know about that.
But you don't care because we're mainly focused on drawing, so.
Yes.
I'm just going to ask on behalf of Tom Spinfield. He says that
Yeah.
do you match your treatment group to controls because you saw another disturbance on the back? The answer is yes. And why not match controls to treatment based on vegetation structural properties?
Because
Oh, sorry, others in the past, not in the past, in the past.
I'm not sure I understand that. Wait, sorry. You match your treatment intervals because you saw another disturbance in the past. So I'm not matching any individual treatment with any individual control. I'm creating two separate groups that are created separately, I guess. So like, first we find all the times where or I guess we do find them at the same time computationally, but basically like we're just going through and we're looking for like, well, which are the times where there happened to be a disturbance in between the two, and which are the times where there happened to be a disturbance outside, and I'm comparing those two groups as a whole. I'm not saying like shot A, like shot pair A versus shot pair B.
There's no matching.
There's no matching involved, yeah. Okay, so after all that computational work, let's see what we got. So if I can click back to my slideshow presentation, yes, okay. So here's a sample of about 20% of the 4 million coincident shot pairs that we found. And you can see two things. So first, well, maybe you can see more. I can see two things. So first, these are falling in these sort of corridors, and that follows the resonance patterns of the orbit of the International Space Station. And I do want to mention here that this graph is not at all to scale. So going back to Jovana's question, these GEDI shots are 25 meters in diameter. I don't know how big those circles are, but that's huge, so that you can see them. But essentially, we're really not actually getting physical overlap between basically any of these shots, even though it looks like that's what's happening here. The second thing is to think about the forests that are being measured here. So in the Amazon, we have what's called the arc of deforestation, where there's lots of human-caused degradation taking place. And then in the Northwest are these much more remote rainforests that are relatively intact. And a lot of our shots are falling in that intact and probably more homogeneous region, which is what we expected and what we were worried about. So now, when I look at the disturbed control and treatment shot pairs, this looks much better, right? Remember, the point of the disturbed control is we want it to be as similar to the treatment group as possible, except GEDI didn't happen to measure the disturbance. And the nice thing to see here is when we look at the spatial distribution of these two, we can now see that actually they are matching up pretty well. So in the end, for the RAD data set, we got about 34,000 pairs in the disturbed control group and 7,000 pairs in the treatment group. Now we get to the best part, which is looking at the data. So are there any more questions about the methods? Yeah.
What is the criteria for them being coincident?
Within 40 meters of one another.
How did you come up with 40 meters?
Good question. So we tested a lot of different distances. Basically, the goals were twofold. Number one, keep as much data as possible. Number two, the coincident shot methods have to work. If there's no disturbance, there should be a one-to-one unbiased relationship, right? And so we're able to basically test using this control group, so we can sort of like look at how, like we can make them further and further apart and see when they start like really not having a good relationship anymore. We also looked at the correlation between the two shots, and we basically said like we want that to be relatively high. And the main thing was we found that if you go from 40 meters apart to 30 meters apart, you lose a ton of data and the correlation increases by 0.01. And we were like, well, that does not seem like it's really worth it. Let's try and keep more data and it's fine to have slightly lower correlation. So that's sort of giving away the results, which I'm about to get to. I can't believe it worked. Okay, so any other questions on the,
Just a follow-up question. Is that 40 meters between the centers?
between the centers?
Okay,
Yeah.
there is actually going to be overlap between them.
So they could have physically overlapped partially, yeah. So there's this kind of like, again, this uncertainty, right? This geolocation error in the shots. So potentially those two shots were further apart than 40 meters because they both fell far away from their reported centers in the wrong direction. Potentially they're much closer than that. Potentially they physically overlapped. And part of the idea also of the 40 meters is that we're saying like, look, because of geolocation error, we don't know, but like even if we tried bringing them to really close to one another, like that actually didn't help us very much because we don't know where these shots truly landed. So we might as well allow a little bit of distance and let's actually make our methods robust to that geolocation error rather than putting really strict requirements on the location.
Maybe you should talk about David Roy's observation about the source of errors in the vibration.
Right. He also pointed out that even that geolocation error, he was like, look, people are stomping around on the International Space Station. And whenever they do that, the sensor is like moving around, doing its little thing. So I think this is what you're referring to, right? So these vibrations are not What he said was, it would have been ideal if this instrument did not have to be mounted on the International Space Station, but it's what we got.
Can you detect how often astronauts go to the
That's the next major thing.
That's actually already that's they was the IoT is got an open security flaw in it, so you can actually.
Oh,
Yeah.
okay, well, never mind, you don't need us.
I just have one question about that. These are codes to show post cloud cover elimination, right? Like
So
what stage of the pipeline is of the GEDI pipeline are you taking these?
Tell me more about it.
So like is it says cloud cover, presume you don't get a good GEDI, or is it?
So this is all post-quality filtering. So actually, there were 12 terabytes of data, and then we like whittled that way down. So there are only about 109 million, about 109 million data points that we are actually considering to be really high quality data. And we did do a lot of work with the folks who are filtering the GEDI data, because it turns out coincident shots are a nice way to figure out if your filter is doing well. So we found before and after filtering, right? Before filtering, these shots are like crazy different from one another. And then after filtering, you can be like, oh, that actually increased the correlation quite a lot. So yeah, I think I saw a question on that.
Sorry, is it also partially like the 40 meters, like, or the distance between less and shot? Is that also first predicated on like you're working with tropical forests? If you're working in a different region, you might have to push those close together to get well correlated ground truth.
Yeah, I think that's a really good point. Yes, I think that part is definitely part of the test, and I think that's why a control is so important when you're doing this. Is you've got to be checking, does your control, like you need a control that's very comparable, right, to your treatment group. Yeah. Yes.
What kind of spatial scale are you considering to be a small scale disturbance? Because
So-
presumably if they could be 40 meters apart, the disturbance has to be larger than that.
No, it doesn't. So, so going back to my fun, presentation here. So we actually only require the second shot to line up perfectly, or as perfectly as we can make it, with the disturbance, right? So the first shot is this kind of predictor from the pre-disturbance state. And then the second shot, we're like, let's get that one to land right there. The smallest, so what we're looking for is 10 to 30 meter size, and that's based on the pixel resolution of the disturbance detection maps. Okay, results, which I've like, wow, totally given away everything. It's supposed to be a surprise. Okay. Woohoo! Okay, so remember our first question, is it possible to use coincident GEDI shots this way? So first sanity check, right? We're gonna look at these control groups, and what we want to see is if there's no intervening disturbance, then we should get that the first shot and the second shot should agree with one another. So here, looking at canopy height, I have the first measurement on the x-axis and the second measurement on the y-axis. And you can see we have pretty good correlation between shot 1 and shot 2, especially in that more homogeneous set of forests on the left, right? And then in the, okay, but then as we expect, the disturbed control on the right is much messier. And I think this is super interesting. We're seeing higher standard deviation, lower correlation, but in both, for canopy height, there's no bias. So the first shot is an unbiased predictor of the second shot. So the relationships for biomass look similar. The variance and standard deviation are a bit higher. And in the disturbed control group, we do see some negative bias, meaning that the second biomass measurement is on average smaller than the first. And this is really interesting because it echoes the idea that was proposed in some papers that came out just a few months ago, that GEDI might be able to measure biomass losses that are taking place in disturbed forests or degraded forests that aren't being picked up by these existing disturbance detection maps. And we're going to come back to that idea if we have time at the end. But moving forward, even with this small bias, we found that when we compared that disturbed control over here to shot pairs that experienced intervening disturbance over here, we found that the differences were substantial. So mean biomass loss and canopy height loss was greater in the treatment group than in the disturbed forest control group. And this held even when we restricted the disturbances to only those where a single pixel in the RAD or the AFC maps was marked as disturbed. Here I'm showing you just the RAD data, but this data doesn't distinguish between deforestation and non-deforestation disturbance. So we also checked with the AFC data set where we're just looking at disturbance, and we basically wanted to make sure, are we just doing a bad job of detecting deforestation? So we looked at disturbances where no other pixel in this kind of surrounding window is marked as deforested. And we still found this statistically significant difference or statistically significant losses. And then in addition, what we're going to look at later is kind of cases where we can actually measure sort of the formal definition of disturbance, which is like there's still canopy cover, but there's also substantial losses. So remember that the variance here is really too high to be looking at any individual disturbance. But if you look at some kind of aggregation, I think you can work with this data. And with these aggregations, I think we have the first large-scale statistically significant evidence that GEDI is measuring biomass and canopy loss following disturbances as small as 30 by 30 meters, which is the smallest size that we were able to measure. Okay, so we were then able to use that coincident shot data set to examine forest structure and how disturbance changes different layers of the canopy. So to see this, we looked at disturbances that are caused by fire specifically, which we can tell from another instrument called MODIS. And what's cool is that it looks like GEDI is identifying sub-canopy fires where the top of canopy height, where mostly the understory is lost. So here in blue are the samples where the top of canopy height doesn't show very large losses after the fire. So you can see like those are falling along that y = X line. But on the right, we see that the understory height does show really big losses in almost all of those samples. And these graphs are very clear, but they're also a bit of a lie. So now I'm going to show you the real story, and we're going to walk you through this. Okay, so we need to talk about plant area index. So plant area index is this unitless measure of sort of vegetation density, like how much space are the leaves and branches and like twigs taking up. So this index, what I have here is in green. Oh, this is where I need my thing. Okay, so but I'll try and show you here. Okay, so in green, what we have is pre-disturbance. So this is the distribution in our coincident shot sets of, for the first shot, what is the PAI? And so you can see in green, there's pretty wide variation in how much vegetation is stored in the upper and mid stories, which is on the left. But it can be quite high. So all the way up to 4, you can see, and a little higher. And the understory, so that's the bottom third or so of the forest, will tend to have less vegetation, even pre-disturbance, but still we've actually got quite a lot. So now if we look at post-disturbance, in red, what we have is what happens to plant area if the fire burned out the canopy and the understory. And you can see here, essentially, both of those distributions are just like really narrowly centered at 0. So basically everything is lost. But then in blue, let's see, sorry, now I'm getting myself lost. Okay, in blue, we have those samples that I highlighted before where the canopy was preserved. And you can see that the understory plant area, which is on the right, is mostly lost, just like in the complete lost case. But the upper and mid stories over here on the left have this diminished but non-zero plant area. So GEDI is showing us these sub-canopy changes in forest structure and non-deforestation disturbances. And I think the other really important thing about this graph is that a lot of research focuses on just that top of canopy height metric. And what we found is that even when the top of canopy height doesn't change, the upper stories can be changing a lot in terms of vegetation loss.
And so if you're using Landsat, you'd only spot the canopy, and so now you can distinguish actual sub-canopy.
Yeah, and we can do this with an actual vertical resolution of about 5 meters. So we can say like, what's happening right in these bands of the forest.
Amazing.
Which is incredible. Okay. So finally, remember,
if you're lucky to have GEDI shot in that space.
yes.
If you're not, if you're unlucky, then nothing.
Then sorry.
Really good.
Yes, I do think, and again, I have to emphasize, you have to look at this data in aggregate, right? At any given spot, I am very uncertain about what happened, right? But you can sort of categorize disturbances and then look at the aggregation and groups, and actually that's what I'm talking about right now. So I'll give you an example of this. So remember that part of the promise of the data set would be that we could use it to extrapolate, right? So we could take biomass losses in we could maybe find biomass losses in disturbances that were not observed by GEDI. So Van Kutsum et al., the authors of that AFC disturbance detection map, also had this semi-proposal for a metric of disturbance intensity that's based on Landsat only. So the idea is, so when they detect disturbances, they classify each Landsat pixel at each timestamp as one of 3 categories, either undisturbed, which I've shown here in green, potential disturbance, which is orange, or not valid, so like sensor error, cloud cover, something like that. And then what they do to make those AFC maps is they use the temporal sequence of those classifications to kind of identify those like overall change patterns. But the raw information, just the number of potential disruption observations divided by the number of valid observations over a fixed time period and averaged over a small area, we think might give us an idea of the disturbance intensity. So we evaluated whether there was any relationship between that metric and GEDI measured percent biomass loss. Again, this is the aggregation, right? I can group disturbances by their intensity, and then I can look at kind of, well, what was the median biomass loss, percent biomass loss in that group. And what we found is that there's actually a decent relationship between these two overall, and near zero disturbance intensity using that metric corresponds to near zero biomass loss or biomass loss approaching the control group. And high intensity goes all the way up to almost 100% biomass loss, which is encouraging. So I think I always have to say, this is very new, and I think there are a lot of reasons to be hesitant about this graph. I think there's a lot more work to do to understand this relationship. So it doesn't account for spatial autocorrelations in the data. We didn't break this down by disturbance type, and we do think that just different types of disturbances are going to look very different. It's also going to be a conservative estimate, especially for small disturbances, and we can talk about that afterward. But I also think that this is a very exciting graph. Because it echoes those earlier results in the literature that said, look, there might be a relationship between what we're seeing in Landsat and disturbance biomass losses. And I think it puts a very promising direction for future work that we could consider finding this. Okay, so in conclusion, GEDI can measure biomass and canopy height losses in non-stand replacing disturbances at least as small as 30 meters by 30 meters using this methodology. We were able to use GEDI to peek under the canopy and measure 3D structural changes following burn events. And we think the coincident shot data set might allow us to extrapolate to disturbances that were observed only by Landsat, but we think there's a lot more work to do here. Yeah. I have a bonus slide, so I guess I have a little time, but maybe should I go for it?
Yeah.
Yay! Okay. Okay, so going back to result number 1, GEDI seems to be measuring subtle losses. So given that GEDI seems to be measuring these subtle losses, I think we should take much more seriously the bias that we observed in the disturbed control group. I think what we're finding is that especially in disturbed type forests, the second biomass measurement is on average smaller than the first, and I think that might be a real result. When we started this project, I thought that one key limitation was that we were only ever going to be able to measure changes in detected disturbances, right? So, and what I mean by that is that like if Landsat didn't detect the disturbance in the first place, then we don't know to look for coincident shots there, and so what are we going to do, right? But the bias is indicating to me that we might actually be measuring changes in undetected disturbances as well. And I think one interesting aspect of this is that another thing we found is that disturbances continue to lose biomass over time in a way that isn't necessarily picked up as a new disturbance in these disturbance detection maps. So this aligns with field data that basically says that depending on the intensity of the disturbance, for years following an initial disturbance, the forest has a really hard time recovering. So we started to look at this with this question of, are we going to be able to, on one side, are we going to see recovery? Like, are we going to see that if there was a longer time between when the disturbance happened, sorry, let me explain what this graph is. Okay, so what we said is basically, we have a disturbance, and that second GEDI shot, we didn't control when it happened, right? It could have been some number of months after, it could have been right after. But we could compare, like, well, what happens if it was right after versus a long time after, and do this kind of, if you're familiar with space for time substitution, this is this general idea. So, and see basically like the further away temporally the GEDI shot is, are you seeing that there's less biomass loss because it's starting to recover, or are you seeing that there's more biomass loss because it's continuing to lose biomass over time? Right? And so what we found, I would say what we found more confidently is the first part of this graph, which is like, we have lots of samples with a really short time, and we're seeing, I think, increased biomass loss for the first year or so. And that is agreeing with field studies that say that like for many types of degradation, there will either be repeated degradation at the same location or just damaged trees will continue to fall and those forests will be more vulnerable to other types of losses afterwards. I'm not sure, so at the end here, maybe we're seeing it level off, maybe we're seeing it begin to recover. That data is super uncertain, as you can see by those massive uncertainty bars. Basically, there's no data there because we only have these 4 years of GEDI data. And so it's very difficult to look at that time range at this point.
It looks like you're getting two groups, one that's recovering and one that's not.
Yeah, it's also possible that different disturbances are behaving differently, right? So we know that we know there are big differences there, right? So like we know that fires look really different from selective logging in this light. And a big paper came out at the beginning of this year that looked at trajectories following disturbance and basically like when does recovery happen, if at all. And so I think there's a lot more to do with this graph, especially because we're going to get more GEDI data. And as we have more data, this only went through 2022. There's a whole other year of GEDI data. I just finished. So I think we can start to look at that. And then GEDI is going to come back. So it's currently in hibernation. It's going to come back. And I think that will also give the opportunity to look at this again.
But you can't overlay wildfire maps onto this because this is a statistical. Can you figure out, so you can figure out the coincidence, let's say wildfires to the coincidence shots?
Yeah, so that's, sorry, I hope I did not make that clear apparently. So that's what we did with these. So these are only disturbances where we know it, well, we don't know it was caused by a fire, but we know there was a fire in that spot at the same time. So I'll say we know it was caused by fire. So these are just the fire disturbance, and we can do that with other types of disturbance as well, but we didn't because that's the next step.
Because floods are the big next one, I guess, right? Because there's loads of flooding in southern Brazil or
We are probably not going to do floods. We're going to do drought and selective logging and fire, which are the 4 major drivers in the Amazon rainforest biome proper. So actually a lot of the Amazon is very flood tolerant and some of it floods seasonally regularly. So yeah, so
it's south, that was a really bad one. The other one off, I think.
yeah, okay.
Okay, let's thank Amelia for
The big question, one of them is, I might have been kind of lost. The disturbance is something that someone else has tracked, or kind of fire maps, etc., or is that empirical from the shots where something is missing?
Someone else has identified.
Yeah, okay. And so about the kind of last point and the subtle loss, like what is the natural way the forest evolves fall into it, right? So I looked at my MRS, I looked at 1 kilometer to 1 kilometer square, which would be about 1,000 GEDI shots that would fit in there, and you would lose, as a big forest, you lose about 40 trees year to year. And so the forest grows slowly, and then there is the breed just drops, right? So that you would expect that in any consecutive GEDI shot, you're not tracking the tiny minute differences of plant growth, but you would be tracking these natural, there's not a disturbance, it's just like regular mortality, right?
I don't think that you're any more likely to see that in your second GEDI shot than your first one though, right? Like if that mortality is
well, the tree never comes back, right? Like it grows slowly. So you've got,
why would your second GEDI shot see that but not your first one? So if there are these gaps in the canopy, which there are, right? Like you would see that you would see a canopy gap in 2019 that was from when it fell in 2017, right? And then in 2020, you would see it like if it's in a sort of steady state, right?
yeah.
You're not going to see a difference between the first and second shot for that.
So
Unless
why I would
there's
expect
action.
always to be like decreasing, because what you're saying is there is like the second shot would always have lower something biomass, etc. And if you extrapolate it, then just the forests are going down, right? Which could be true, which could just, but it also could mean that you're never going to see a tree that was dropped and suddenly fills in the gap, right? So the plant growth is slow and then the tree falls down. Like if you think about what happens with natural mortality, like okay, most of the times you would find the gap, but if you are lucky that you would actually spot the occurrence of the natural mortality of a tree, that would provide a negative bias to your data, right?
I'm not sure I see why that would particularly affect the second GEDI shot.
Well, you were never going to see two GEDI shots where the first one has the tree missing and the second one appears, right?
Yeah, you could, right? Because if the first one fell in that canopy gap, then in the second one, it's gonna look like it grew a lot, right? Which it didn't. But you
But
would,
the second shot is always like,
it's temporally after, but it's not exactly in the same location, right? So like,
oh yeah,
if you have
okay, yeah.
some chance of falling in a
Yeah,
canopy
sorry.
gap both times.
This is the nuance
Right.
of the kind of.
Yes,
matching
exactly. It's
beauty.
quite tricky to wrap your head around, but this is this idea of like, why, like your first and second shot are like the same, except for what, right? And so that's how you manage to be robust to that geolocation uncertainty, is that you basically say, well, that shouldn't affect the first and second shot differently. The other thing I think is interesting about that is that we see this much more in the disturbed forest than in the control group that are mostly intact, right? So we're seeing a different effect, right? And we're seeing more of this bias where we have, where we think that there might be unlit losses. Yeah.
I class this technique as extremely funny, but I'm trying to figure out if you can generalize to any other instruments, because it's such a unique coincidence of the fact that GEDI is an IFS and it's not wall to wall. So do you think this would apply to any other instruments that you've seen, or drawing, for example, but GTSR and so on?
I mean, possibly, right? Like it's kind of, I think it's a really neat way of taking anything where you have a sample, right? And trying to understand how to go from a sample to an overall like extrapolation. I think ISAT is another one that has kind of this question, though they do not really have the geolocation uncertainty problem. Yeah. But I think, yeah, it's a fun technique. The other fun fact about this is that, so GEDI was really supposed to get good coverage, not do coincident shots, right? But get good and even coverage. And it was really not supposed to look like that, right? But the International Space Station, unbeknownst to the NASA scientists, to save fuel, went to a higher altitude, right? Thinner atmosphere, less fuel. And as a result, ended up basically tracing these resonance patterns in these corridors again and again and again. And no one noticed this for like a year. And then when they did notice it, they were like, hey, could you like lower the International Space Station? And they were like, no. In the end, they did lower it a little bit so that GEDI could get more coverage. This was a huge problem for the GEDI mission, because in order for, like, what their goal was is to create a complete like 1 kilometer resolution map, and they had just no data in these like huge sections, right, where they weren't seeing it. So I think what was kind of unfortunate turns out to actually be really nice for a different type of analysis.
Lemon through lemonade.
Yeah. Yes, Jan.
So very interesting talk. I know that you display a very interesting slide for the shift of the histogram from the right to the left after the understory disturbance.
Yeah.
And this information be used to give estimation of the carbon loss of the understory forest.
I don't know. I'm not sure how plant area index translates to that. And so I'm sticking with the biomass estimates for now, but yeah, I'm not sure. But I guess I do think that the plant area index is probably more reliable than biomass as a measurement from GEDI. So that's why I like these graphs a lot, because I think that they are a very good metric.
I think David Coombs can be the person to answer.
Yeah.
Yeah, to biomass. The other
Are we still relying here to some degree, or like assuming some force homogeneity?
Yes.
Because what would happen, what's your intuition that would happen in a highly fragmented forest with a lot of gaps? Would this kind of analysis even be possible? We would have to be like 5 meter difference between 2 GEDI shots or something.
Yeah, it's a really good point. So I think, yeah, like you do need the first shot to be a good predictor of the second shot. I think what's interesting is that ultimately a lot of our analysis is now relying on this bias, which actually works even in a fragmented forest, because it's a way of looking at changes, right? Like, again, it's this question of why would the second shot be more likely to land on nothing than the first shot unless something changed, right, in the area. And so I think to a certain extent, we can handle pretty heterogeneous forest as long as there's no systematic reason why you're always sampling like one piece of that before and one piece of it after, right? That said, like, yes, I agree. I think the more that happens, right, the more variance you're gonna see in the control group. And at a certain point, that variance could just drown out the signal that you're seeing, and you could just kind of be like, I have no idea.
Right, because it could just be in this huge aggregate
Yes.
group, we're seeing it's lower, but if you choose a different group, it's gonna go up, and then it's just like actually just noise.
Exactly. And so like when we thought about abandoning the project was before we got the good filtering. And so there we were like, well, these correlations like aren't even good enough. You can't even say that these two GEDI shots measured the same thing. So we thought that the level of heterogeneity that was just normally there was too much for the instrument. And then we found that actually that was because of the instrument and not because of the forest. But I think the same principle would apply if it's too heterogeneous. Yeah.
You said you can't compare individual comparisons of the shots, but like at what, I'm sure, I guess the more data you include, the more confident you can be.
Yes.
What kind of spatial scale do you think you could use these results to look at? Does it have to be like the whole of the Amazon?
Yes, I think it's, so what we're trying to do is, that is statistical analysis that I'm about to embark on, because basically the next question is, well, how much can you break down this data before you're kind of like, oh, you're looking at some crazy stuff here. So what we are next gonna do is, because we wanna basically extend those, like really study that intensity graph. And we wanna see, like, could we look at different types of disturbance? Could we look at maybe different regions? So the first thing we're doing is getting more data. So we're gonna try and download data for all of the tropics. And we're gonna get all of the GEDI mission data through the end of 2023. And that's gonna give us a lot more stuff to work with. So like super anecdotally, those uncertainty bars are absolutely massive once you get to fewer than about 100 pairs per group. But again, like that's pretty anecdotal. And I think we need to do like basically formal analysis of this, but it's doable, right? Because you just need to say like, if I compare it to a control, like what's the variance there, what's the variance here? Yeah. Yeah.
Maybe we need to get NASA to make small mistakes. With a telescope, but we have to calibrate it, so trying to line, so starting something we have ground too, but the revelation would be also.
We pointed the wrong
Should I then read out Tom's second question then?
Yeah.
Because he really would like to do matching. It's vegetation structural properties as opposed to, what you're doing, it's not quite matching.
I guess my concern about matching is this problem with like an individual, what is the meaning of an individual data point here, right? Like I can't say, like sometimes we see totally unrealistic things, right? Like it's like 0 biomass to 300 meter biomass, which I think is what Petter's pointing out, right? Like sometimes you fell in a canopy gap and it is what it is, right? And so if I match that with another case that has similar vegetation properties, like what is the meaning of that, I guess? But you could do matching in these aggregated groups, I guess. So maybe we could talk more about that. Like you can kind of like, you could say, all right, here are these whole sections of the Amazon that are interesting to look at together. And we should be like doing a control group and a treatment group for that section.
You've done that with the fire.
And it's right, done this with fire. So these breakdowns of like, I care about similar disturbance types. I care about similar disturbance intensities. I care about similar disturbance extents. I care about similar time sense disturbance and so on. So you can do those breakdowns, and we could do something similar where we say, I care about similar types of rainforest and vegetation as well.
Okay. Great, I think we're done with questions. Thank you. Also, please do come in at 12:30 next week.
You're welcome.